I'm Norman Wildberger. Today's famous math problem, the 8th one in our series, goes back to Leonhard Euler, who asked, how many ways can one subdivide an n-gon into triangles? So let's illustrate this with some examples. An n-gon is just a polygon with n sides, and the simplest one is a triangle with 3 sides, and there's only one way of subdividing it into triangles, namely itself. With a 4-gon, which you can think of as a quadrilateral, and we'll represent it here as a square, you can subdivide it in 2 ways. You can draw a diagonal in that direction or a diagonal in that direction. So we'll count this as 2, and for a reason that I will explain in a little while, we're going to call this number C sub 2. It's actually the second Catalan number. This one's the first Catalan number. Then after that we move to the case of a pentagon, and then there are 5 ways of subdividing a pentagon into triangles. Basically one way for each vertex. At each vertex you're allowed to make sort of 2 diagonals that proceed from it, and there are 5 vertices, and so there are 5 sort of symmetrically placed ways of subdividing a pentagon. For the hexagon it becomes a little bit more interesting, where there's 14 different ways. Let's have a look at them. All right, so one way is to take a vertex and to draw diagonals from that vertex. Obviously there are 6 ways of doing that, corresponding to the 6 vertices. And then another way is to draw sort of 2 parallel diagonals, these ones here, and another diagonal that's sort of transversal between them. So 2 parallel diagonals can be chosen in one of 3 ways. There's this set of parallels, or there's this set of parallels, or there's this set of parallels. And for each one of those ways, there's 2 ways of choosing a sort of transverse diagonal, either this way or this way, for example. And either this one here, or this one, and this one, or this one. And then there are 2 more ways of triangulating this hexagon by essentially inscribing a triangle, and we can do that in one of 2 different ways. Altogether, 14 different ways. It might be a fun exercise for you to try to count how many ways there are of triangulating a septagon, a 7-sided polygon. So this problem was posed by Leonhard Euler, who lived from 1707 to 1783, in a letter to Christian Goldbach in 1751. In the 18th century and in the 17th century previous, mathematicians often communicated thoughts and ideas and results by letters to other mathematicians. And these letters would be actually quite valuable documents that would in some cases be copied and sent to other mathematicians or distributed informally. Leonhard Euler is, in my opinion, the greatest and most important mathematician of modern times, and ranks second only to Archimedes in terms of being the greatest mind of all time. And for those who might argue that Euler was greater than Archimedes, I think it's a bit of a toss-up. They were quite different figures at different times. But certainly in modern times, it's hard to go past Leonhard Euler, whose output was just phenomenal and who had such a vast insight into so many different areas of mathematics and physics. His influence on the modern world is very profound and deep. So he was a Swiss mathematician, born originally in Basel, but he worked most of his life in Berlin and in Russia, in St. Petersburg. He was a bit of a child prodigy and was recognized by Johann Bernoulli, who was the prominent mathematician of his day, as his protege, and was tutored by him. So he got very high quality instruction at a very early age. He's done foundational work in so many things, it's hard to think of an area of mathematics in which he didn't make some kind of direct or indirect contribution. In analysis, in number theory, graph theory, calculus of variations, in astronomy, many other aspects of applied mathematics. He generated lots of important formulas. Some of his formulas are the most well-known formulas in mathematics. E to the pi I plus 1 equals 0. Very famous and beloved formula that involves the 5 most important constants, generally speaking, that people recognize in mathematics, all in one equation. V minus E plus F equals 2. The relation between the vertices, edges, and faces of a polyhedron. And then this summation of the series 1 over n squared, miraculously giving this number pi squared over 6. And perhaps we can summarize people's approach to Euler by this famous quotation of Laplace, who said, read Euler, he is the master of us all." So Euler will figure quite prominently in this series because he generated so much mathematics and many interesting problems too. The notation that we use to describe the numbers that appear in Euler's problem is due to a later mathematician, Catalan. And they're usually called the Catalan numbers, although in fact Euler was the first person to really study them. If we named everything after Euler that he discovered, too many things would have Euler's name on them and it would get very confusing. All right, so here are the Catalan numbers. So Cn is the number of triangulations of an n plus 2 gon. So that means the case of a triangle corresponds to n equals 1. That's just our notational device. So the number of ways of doing a triangle is 1. Number of ways of triangulating a quadrilateral is 2. A pentagon, 5. Hexagon, 14. And septagon, 42. Octagon, 132. Nonagon, 429. Decagon, 1430. And maybe onagon, I'm not sure what we'd call an 11gon, 4862. And of course the sequence carries on. It's a very famous sequence of Catalan numbers. In Sloan's online encyclopedia of integer sequences, it's the sequence A000108. Sloan's online encyclopedia of integer sequences is a fabulous tool and resource for mathematicians that I've talked about in my other series, and it's well worth checking out. And this particular sequence is probably the one that has the most description of all the sequences in Sloan's encyclopedia. It's a measure of the importance and the universality of this particular sequence of numbers, the Catalan numbers. So after Euler posed the problem, a fellow called Segner discovered the following very pleasant recursive way of computing these things. So this is a more efficient way of calculating higher Catalan numbers instead of drawing big polygons and trying to count all the number of triangulations. The formula is that the nth Catalan number is a sum from k equals 0 to n minus 1 of a product of ck times cn minus k minus 1. So it expresses Cn in terms of the previous Catalan numbers. For example, if n is equal to 6, then we have a sum from k equals 0 to 5. And the sum is this one here. It's C0 times C5, C1 times C4, C2 times C3, C3 times C2, C4 times C1, and C5 times C0. All of those added up. So for example, if we knew the ones up from 1 up to 5, we could calculate C6 by using this formula. But the formula also involves this perhaps curious Catalan number, C0. Now C0 technically would correspond to the number of triangulations of a 2-gon, which is just a segment. That doesn't seem to make much sense. So we define C0 to be 1 for convenience and to make the formulas involving the Catalan numbers work. All right, so this 0th entry is sort of by definition, we define C0 to be 1. All right, so how does Segner's recursive formula then work? So C6 would be the product of C0 times C5, so 1 times 42, plus 1 times 14, plus 2 times 5, plus 5 times 2, plus 14 times 1, plus 42 times 1. Good. Sort of nice sequence of products. There they are there, and you can add them up, and you get 132. So that's one way of getting the sixth one if we know the first ones before that. So why is Segner's formula valid? Well, let's have a look at the geometrical meaning. Remember what C sub 6 is. It's the number of triangulations of a 8-gon. So here's an octagon. And let's distinguish a base. So let's sort of color one side green, sort of to anchor the octagon. And let's label these other vertices 0, 1, 2, 3, 4, and 5. Okay, now let's think about all the possible triangulations of this octagon and just concern ourselves to start with the triangle that includes this side. So of all the triangles that appear, exactly one of them will have this side as one of its three sides. So the other vertex can be any one of these other 6 vertices. So the triangle could be this one, and this one, or this one, and this one, and this one, or this one, and then this one, and this one, which is one that I've shown you. Or the other vertex could be here, here, or here. So let's just consider one of those possibilities, say this one here. Well, if that's one of the triangles that's appearing in the triangulation, then how many ways are there of filling in the rest of the triangulation? Well, what we see is that on this side here we have a 4-gon, and over here we have a 1, 2, 3, 4, 5, pentagon. So basically we can triangulate this 4-gon in any number of 2 ways, and we can triangulate this pentagon in any number of 5 ways. So there's 2 possible ways of triangulating the thing on this side, and 5 possible ways of triangulating what's on this side. And so the number of ways of triangulating this thing, if this is an included triangle, will be 2 times 5. And that's exactly why this sum end appears here. The 2 times 5 is representing all those triangulations that include this particular triangle from our base. And then we can see that these other terms just correspond to corresponding other products where we've chosen other vertices other than this one. That's a geometrical explanation of why this formula is very reasonable and a natural formula that allows us to recursively compute the Catalan numbers. Okay, so what about the answer to Euler's problem? What is a formula for this number C sub n? Well, Euler found such a formula. It was a few years after he posed the problem. Here is Euler's formula for C sub n. 2 times 6 times 10 times all the way up to 4n minus 2 divided by n plus 1 factorial. So the numbers here are all increasing by 4, starting with 2. And the biggest one is 4n minus 2, and is the index here. That was Euler's formula. He proved it by a lengthy and rather laborious induction argument. It is not at all so easy to establish. And I'm going to leave it to you as an exercise. You might want to tackle this problem. It's quite a serious problem to prove this formula, even if you know in advance what the formula is. So I give it a D equals 4 rating, quite high on our scale in terms of difficulty. Now I'm going to later in this video give you a derivation of this, but it's not at all like Euler's derivation. Some easier exercises is to show that this formula is equivalent or can be rewritten in 2 different ways. So another formula for it is that it's 1 over n plus 1 times the binomial coefficient 2n choose n. All right, so that's an exercise. Shouldn't take you more than an hour to do that, roughly. 2n choose n, I remind you that that's 2n factorial divided by n factorial times n factorial. This is a binomial coefficient, and what we're doing is we're taking 1 over n plus 1 times that. It's certainly not obvious from this formula that n plus 1 divides this number. But if this formula is true, then this has to be an integer because it's counting the number of triangulations of an n plus 2 gon. So there's something a little bit surprising about this formula, the fact that it implies that n plus 1 divides this particular binomial coefficient. And there's a variant on this formula. Show that Cn is equal to the difference between two binomial coefficients. 2n choose n minus 2n choose n plus 1. This makes it obvious that this thing is actually an integer. It actually shows that it's actually obtainable as the difference of essentially two adjacent elements in the Pascal triangle. So you can read off the Catalan numbers pretty easily if you have a Pascal triangle in front of you. All right, so those are some challenges. These are relatively easy. This one is a more serious challenge. From Euler's formula for Cn, we can pretty easily see that Cn plus 1 is 4n plus 2 divided by n plus 2 times C sub n. Just the form of the formula makes this almost immediate. So this is a simpler kind of recurrence. It tells you that to get the n plus first Catalan number, all what you really need is the nth Catalan number. You don't need all of them, as in Segner's formula. On the other hand, you have to multiply by this somewhat more complicated rational expression involving n. Conversely, if we manage to establish this recurrence, then together with the obvious initial statement that C sub 1 equals 1, we'll be able to prove Euler's theorem. Because then we can just generate these one at a time by multiplying by constants like this, and that will generate exactly Euler's formula for us. So Euler's formula is pretty close to being equivalent to this recurrence. And so to prove Euler's formula, which is what we're going to do now, we're going to prove this recurrence. So we want to show that if Cn is the number of triangulations of an n plus 2 gon, then 4n plus 2 times Cn equals n plus 2 times Cn plus 1. We're just rewriting this formula like this. That's what we want to prove. We want to prove that this number is equal to this number for any n. All right, so let's sketch a proof of this equality. And we're going to adopt the combinatorialist's point of view, which is that when you want to establish an identity like this, one way of doing it is to find two sets of combinatorial objects, typically, that each represent or that have the sizes of the numbers on either side of the equation. And then once we have these two sets, we want to establish a bijection between them. We want to see combinatorially that you can naturally link up each element from one set to another element in the second set. So we're going to pair up these two sets, showing that the numbers of elements in them has to be the same. All right, it's a strategy. So what we want to do is we want to find a bijection between two sets, one of them having this number of elements and another having this number of elements. All right, so let's look at this side first. C sub n is the number of ways of triangulating an n plus 2 gon. So let's imagine that here's an n plus 2 gon. I'm going to use n equals 6 for the purposes of illustration, although the argument is quite general. So here's an n plus 2 gon, and to orient ourselves, let's denote or choose one particular side and call it the base. We'll color it something and say that's the base of our n plus 2 gon. Okay, and then we're going to consider a triangulation of it. And there are C sub n different triangulations of this thing. Now once we have a triangulation of this n plus 2 gon, how many edges are involved altogether? Well, there are the original n plus 2 edges along the outside of the polygon itself. And then there are the edges involved in our triangulation. So here with this 8 gon, we see that sort of the triangulation involves these new edges. There's 1, 2, 3, 4, 5 of them. In general, that's going to be the case. There's always 3 less interior edges in a triangulation than there are edges around the outside. So there are n plus 2 edges around the outside, and then there will be n minus 1 edges in the triangulation. You might like to convince yourself of that. Altogether then, there are n plus 2 plus n minus 1, in other words 2n plus 1 different edges in the triangulation when we include the external edges and the internal edges. That's good because 2n plus 1 is a factor of this. There's only a factor of 2 more that we have to sort of introduce, and we're going to do that by choosing one of these edges and directing it. So you get to choose one of these edges, and it doesn't matter which one, it can be any edge, and then you direct it. You decide either a direction, this direction or this direction. All right, so I happen to have chosen this direction, and I've made it thick and colored in red. That's my chosen edge, and I've directed it in this way, so it's going from here to here. So the number of ways of doing that is 2 times 2n plus 1 times cn. It's exactly this number. And let me just summarize why that is. Because the number of triangulations is c sub n. The number of ways of choosing one of the edges is 2n plus 1. And the number of ways of choosing a direction for that chosen edge is 2. So there are 2 times 2n plus 1 times cn, such configurations involving a triangulation and a chosen directed edge. Okay, now how about this quantity, n plus 2 times cn plus 1? Well, the cn plus 1 is the number of triangulations of an n plus 3 gon. So here's an n plus 3 gon, which in our case will be a 9 gon. 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll choose a base. And then what we're going to do is we're going to choose one of the non-base sides around the outside. So there are n plus 2 edges around the outside, not including the base. And we're going to choose one, say that one there. All right. And the choice of number of ways of doing that is n plus 2 times cn plus 1. So we've chosen a triangulation together with a distinguished non-base side on the outside. So there's 4n plus 2 times cn different configurations like this. There's n plus 2 times cn plus 1 different configurations like this. Now to prove that these two numbers are the same, what we're going to do is establish a bijection between this set and this set. In other words, I'm going to show you how to match up every one of this kind of diagram with one of this kind of diagram. And I hope that the example that I've shown you here makes it a little bit suggestive what I'm going to do. You can see that these are almost the same, except that where the thickened red edge was here, we've kind of popped it open to make a new triangle with this new side inserted. The rest of the triangulation is as before. So these ones here are just like there, and these ones here are just like over here. So basically we've taken this thing here and we've opened up that edge by essentially sort of expanding that vertex and adding a new edge right at that vertex. And how did we know to choose this vertex and not this one? Because we're going to choose it at the head of the direction of the edge that we've got. All right, so that's how to go from one of these to one of these. On the other hand, if we start with one of these and we have this distinguished non-base side, well, then we're just going to take the triangle that it appears in. It appears in some triangle in this triangulation. And we're just going to collapse that triangle by essentially identifying these two things, bringing it together, collapsing these two sides to get a triangulation of the n plus 2-gon. So have a think about it. Maybe you could draw some diagrams, convince yourself that this always works. Even if this edge is, say, on the edge, even if it's the base down here. And it provides a bijection between these configurations and these configurations, and establishes for us then that this number equals this number. And that's essentially the recursive formulation of the Catalan numbers that's equivalent to Euler's formula. As a sort of modern day bijective proof of Euler's formula. So what makes the Catalan sequence so enticing is that there are so many different ways of arriving at essentially the same sequence. Euler's original formulation in terms of triangulation of a polygon is only one of many, many, many different ways that combinatorialists now understand this sequence. And in Richard Stanley's sort of Bible of enumerative combinatorics, there's a large section devoted to Catalan numbers and various equivalent formulations of it. I think there's something like 60 or 70 different versions or aspects or incarnations of the Catalan sequence that he lists. So I'm just going to show you a few additional incarnations of these very interesting numbers. The first one is Catalan's actual thinking about this sequence. It's the number of ways of parenthesizing n applications of a binary operator. That's a long-winded way of saying that. Suppose you want to multiply four numbers, a, b, c, and d together, and you insist that the numbers be in this order, a, b, c, d. But you don't insist on which two numbers you're going to multiply together at any one given time. So multiplication is a binary operation. You can only multiply together two things at any one time. So there are quite a lot of different ways of deciding on the ordering of these different four numbers. For example, we could multiply a, b together first, and then we could multiply that by c, and then we could multiply all of that by d. Or here, we could multiply a by the product of b and c, and then all of that we could multiply by d. Or we could multiply a times b together, we could multiply c times d together, and then multiply those. Or here's a times the product of bc with d, and here's the product of a with the product b times cd. Those are the 5 ways of parenthesizing So those are the 5 ways of parenthesizing essentially these 3 multiplications amongst the 4 objects. And to give you an idea of why this might be the same as Euler's triangulation kind of counting scenario, I've associated to each one of these multiplications a pentagon with a triangulation and sort of as a base side here on the bottom. And the sides otherwise are called A, B, and C, D. And if you sort of read this thing from left to right, in terms of what this product here is, then I hope you can perhaps see that this thing is corresponding with this. Might leave it as a challenge for you to figure out exactly how to enunciate this correspondence and to generalize it to higher n. Another incarnation of the Catalan numbers is in counting Dyke words. These are words formed by having n L's and n R's, forming a word, with the property that every initial string has at least as many L's as R's. So we're looking at a string of L's and R's with an equal number of L's and R's, and altogether n L's and n R's. But it should have the following property, that as we keep going from left to right, at every stage, if we're counting the number of L's and R's, we always have at least as many L's as R's. So the number of L's dominates the number of R's all the way through. So for example, there are 5 such possibilities when we have 3 L's and 3 R's. This obviously works. Here we have L, L, R. So at this stage the L's still dominate. Then when we include another L, still dominates, and continuing. Here L, R, L, L, R, R. Here L, R, L, R. Okay, at this stage they're equal. That's still all right. But at no stage do we have more R's than we have L's. And there are exactly 5 such possibilities. All right, you might like to write out all the Dyke words when n is equal to 4. And you might like to give a bijection between these Dyke words and the parenthesized expressions that we were looking at on the previous page. These Dyke words correspond to an interesting, sort of amusing walk kind of counting problem, where you have a drunken person who is taking random steps, and we're counting how many steps or how many paths he can take, where he's going to take, say, 6 steps altogether and come back to where he started, but he has a bit of a problem in that he's at the edge of a cliff, so that if he ever takes a step beyond there, he's going to fall off that cliff. That's essentially the condition, that the number of left steps should always be at least as much as the number of right steps. So for example, the sequence L, L, R, L, R, R corresponds to the walk where he does a left step, another left step, a right step, another left step, and then 2 right steps to get back to where he started. And he's managed to do that without falling over the cliff. That's another interpretation of what these Dyke paths are counting. They're counting random walks with a particular kind of constrained nature. He's only allowed to go in that direction. Now, by just changing our interpretation of the Dyke words, we get a 2-dimensional manifestation of the Catalan numbers in terms of walks on a grid. So if we replace the L's in a Dyke word with U's, standing for, say, up, then the Dyke words count paths from one corner, southwest corner, to the opposite corner, the northeast corner of a square. And these paths are distinguished by having the property that they never go below the diagonal. So for example, if we have n equals 3 case, then we're working in a 3 by 3 square. We're walking from here to here. And then say this one here, U, 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 R, 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 which corresponds to one of the Dyke paths in the previous page, but with the L's replaced with U's, now corresponds to the path up, 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 right, right, right. This one here is up, up, right, right. This one up, up, right, right, up, right. Up, right, right, and up, right, right. So exactly 5 paths that you can take from here to here, where at each stage you're either going up or right, but you agree to never go below the diagonal. You're allowed to land on the diagonal, but you're not allowed to venture on the other side of the diagonal. So in terms of the combinatorics, the total number of paths from here to here is 6 choose 3. because altogether there are 6 steps that you have to take. You have to take 3 ups and 3 rights. And a path is determined by where in those 6 positions the 3 ups are going to be, for example. So there's 6 choose 3 different paths altogether from here to here, including paths that go above or below the diagonal. That number happens to be 20, since it's 6 times 5 times 4 divided by 3 factorial. Same as 5 times 4, 20. On the other hand, these Dyke paths, that's our Catalan number. And our formula is 1/4 6 choose 3. So 20 divided by 4 is 5. And this is telling us that 1/4 of all the total number of paths have this property that they stay above or on the diagonal. And of course, there's a corresponding statement to be made if the square is bigger. It's sort of interesting that you get a nice fraction of all the paths represented by these restricted paths staying above the diagonal. The third new aspect of the Catalan numbers that I'd like to tell you about is its connection with things called young tableau. These are lovely combinatorial objects that figure very prominently in group theory and a related subject called representation theory, which I actually studied for many years. I have a great love of young tableau. All right, so these are rather restricted young tableaus. They're ones with diagram which are 2 by n rectangles. So what is a young tableau? So here's a 2 by n rectangle. Again, we're going to stick with the case when n is equal to 3. So we have this 2 by 3 box, and what a young tableau is a filling of this box with the numbers from 1 through 6, which has the property that as you move right, the numbers are all increasing, and as you move down, the numbers are always increasing. So here's one way, 1, 2, 3, 4, 5, 6. If we go right at any stage, we're increasing. If we go down at any stage, we're increasing. But there are some other ways of doing this as well. For example, this 1, 2, 3, 4, 5, 6. Still increasing along this row, still increasing along this row, and increasing down any one of the columns. Another one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 5, 4, 6. 1, 3, 2, 4, 5, 6. And you might like to verify that if you have an n equals 4 situation, so if you have a 2 by 4 diagram and you count the young tableau, that you get also the 4th Catalan number, 14. And you can try proving this by finding a bijection between young tableau and any one of the previous aspects of Catalan numbers we've talked about. Finally, I'd like to mention very briefly an aspect of sequences that links combinatorics in a very profound way with algebra. And this is usually called the theory of generating functions, although I would prefer to use the term generating series because I think that's really more what's going on. So the idea here is that to something like the Catalan numbers, we associate a polynomial, but rather a special polynomial that has higher and higher powers of, say, alpha in them. So the various coefficients of the various powers of alpha record the elements in your sequence. It's the basic idea of a generating function. And now it's an interesting exercise to show that Segner's recursive relation between the Catalan numbers essentially amounts to this algebraic relation enjoyed by this generating series. That the series is equal to what you get when you take 1 plus alpha times the series squared. And when we square it, what we're doing is we're treating it as a polynomial and just doing polynomial arithmetic with it. From this, we can deduce an interesting and suggestive formula. You can solve for C alpha, because it's essentially a quadratic equation, to get an expression of the form C alpha equals 1 minus square root 1 minus 4 alpha over 2 alpha. Now, once you've done that, and that's another exercise, then you might say, well, what's going on? What does this mean? Well, it turns out that this square root, 1 minus 4 alpha, is not to be thought of as a square root of real numbers. It's a square root in an algebraic sense. And Newton made very clear what this means. So there's a way of using Newton's binomial theorem, which is sort of an extension of Omar Khayyam's binomial theorem, to expand this out and essentially recover the formula for the Catalan numbers. We're going to talk more about Newton's extension of the binomial theorem. It's another important problem that will appear at some point on this list. So we'll return to this question here to connect the Catalan numbers with this intriguing looking expression. So we see that the Catalan numbers are connected with lots of things, and in fact there are a lot more aspects of the Catalan numbers. New ways of interpreting them are still being discovered every so often. And for a good survey and a sense of the richness of that, I suggest that you have a look at Sloan's online encyclopedia of integer sequence, A000108. In our next famous math problems video, we're going to look at a very ancient and much studied problem. The astronomical issue of how far the moon and the sun are actually from the Earth. That's a very interesting, long-standing problem that goes back to the ancient Greeks. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.